I welcome all of you to the lecture on flow in a pipe. This lecture will be presented for laminar flow in a pipe, then turbulent flow in a pipe, and finally minor losses for flow in a pipe. For the laminar flow in a pipe, the analytical expressions derived for fully developed flow will be presented. For the turbulent flow in a pipe, the results will be presented mostly from experimental study, and the pressure drop that occurs in a laminar and turbulent flow corresponds to the major loss. And when we have a pipeline, we also have certain connections, like whenever there's a turn in the along the path of the flow, this pipe acts like a conveyor belt to transport liquid or gases from one place to another. So while during the passage, we may have certain turns. So there are like 90-degree turns, or there are certain connections. We also have certain walls. So whenever we have those connections, there are certain pressure loss which occurs through those connections and through those walls. So the pressure loss to the pipes will be presented as a major loss, and the pressure loss which occurs when it passes through the connections and the walls will be presented as minor loss. Before we start, let us discuss the difference between the laminar and turbulent flow. There is a famous experiment by Reynolds where a dye is injected in a laminar flow and a turbulent flow, and the trace of the injected dye is observed to classify the two types of flow. So if you consider a flow which is laminar, and along the path of the flow, if a dye is injected, then it is found this dye is a neutrally buoyant particles, and it just follows the path of the fluid particle. So in a laminar flow, you can see that the dye remains horizontal, which indicates that a fluid particle in a particular horizontal layer is moving along its horizontal layer, and there is no transverse velocity. And in this case, when you have a uniform flow, here this is a problem which corresponds to a laminar flow where you have a horizontal velocity. So in this case, in a laminar flow, the dye moves along a straight path, which indicates that the fluid particle moving in this horizontal layer remains in that layer. Whereas in a turbulent flow, when the fluid particle is, this is a problem corresponding to a horizontal flow where the velocity is large enough. When you keep increasing the inlet velocities, then flow transits from the laminar flow to a turbulent flow. And if it's a turbulent flow, then in that case, when you inject a dye, then when the fluid particle is moving on a particular plane, there is a velocity fluctuation, there is a transverse velocity, the vertical velocity fluctuations which acts and which results in the zigzag motion of the dye as shown here. This is a signature of a turbulent flow when we inject a dye in a turbulent flow. So this is a famous Reynolds experiment by which the laminar and turbulent flows are you can detect these two types of flows. Laminar flow has a characteristics of you have a smooth streamline and you have a highly ordered motion, where turbulent flow is characterized by the velocity fluctuation and there is a highly disordered motion. So as I mentioned that when the flow velocities increases, the transition from laminar to turbulent flow occurs. However, along with the velocity, there are other variables which also play a role, such as viscosity and the density of the fluid, and the characteristic dimension corresponding. So if you consider flow in a pipe of diameter d, where the average inlet velocity is u average, then for this case, here I'm showing you the definition of a Reynold number. the Reynold number is defined as the ratio of the inertia force to the viscous force. Inertia force is expressed by the momentum flow rate. So if you consider flow in a pipe whose characteristic dimension is the diameter of the pipe shown here as d, and the inlet average velocity is u average, then if you want to represent the scale of the inertia force which corresponds to the momentum flow rate. So if you consider, let us say, axial momentum flow rate, the axial momentum flow rate will be given as by the product of the mass flow rate and the axial velocity, which is u average. Now the mass flow rate can be expressed as density into area into velocity. Area is expressed in terms of the characteristic length scale, which is the diameter of the pipe. So in a two-dimensional flow, the area is expressed in terms of the product of the length scale, which is d square. So this is a representative mass flow rate, which is given by a density of product of density area expressed in terms of d square in terms of scales, and this is the velocity. So this is a representative scale of the mass flow rate. So when you take the product of the mass flow rate with the axial velocity, this gives you the axial momentum flow rate, which corresponds to the inertia force, and divided by the viscous force. The viscous force is expressed in terms of the viscous stress into area. The scale of the viscous stress is given by mu into velocity gradient. So the velocity gradient is scaled as the ratio of the velocity and the length scale, so which is u average by d. So this is a representative scale of the viscous stress, and area, the scale of area is expressed in terms of d square. So when you take the ratio of these two, the d square cancels down from the numerator and denominator. This u average also cancels down, and you get rho rho u average into d divided by mu. So this is defined. This is the ratio of the inertia force and the viscous force, called as Reynold number, and it is expressed in terms of the product of density average velocity, which is the characteristic velocity scale, the characteristic length scale, divided by mu. If this Reynold number is for flow in a pipe, it has been found that if the Reynold number is less than 2300, then the flow is laminar. For Reynold number between 4000 to 2000, it's a transitional flow. The flow is transiting from the laminar to the turbulent flow. And for a Reynold number greater than 4000, the flow is turbulent. So after the introduction of the laminar and turbulent flow, I'll start with laminar flow in a pipe, then I'll go to the turbulent flow in a pipe, and finally I'll discuss the minor losses. So for laminar flow in a pipe, I'll start with discussing the physics of flow development, and then I'll discuss the two types of non-dimensional pressure, non-dimensional variables, which are called as friction factor, and then I'll discuss the pressure drop, head loss, and pumping power, and finally I'll discuss the friction factor for a non-circular pipe. When we consider flow in a pipe where this x direction is the axial direction, this r is the radial direction, the velocity in the axial direction is represented by u, the velocity in the radial direction is represented by v, and if you have a uniform velocity at the inlet, then when the fluid enters the pipe, then at the solid surface you have a boundary condition which is called as no slip condition. So due to the no slip condition, the fluid velocity at the stationary bottom wall, stationary solid wall, is 0. The fluid is entering with a constant velocity. So, and there is a stickiness between the different layers of the fluid. The fluid which comes into the contact with the walls of the pipe, its velocity is 0. But since the fluid is entering with a larger velocity, there is due to the stickiness of the fluid, the above the above layer, there is a decrease in the velocity, and slowly there is a velocity gradient which sets in. The velocity gradient is sets in from the this velocity gradient is shown from one of the wall. This is a cross-sectional view which is shown. The velocity gradient also sets in from the other end of the wall. This is from one end of the wall. This is from the other end of the wall. And this is the actual velocity profile which is observed at an actual location, which is shown here. If you go to a downstream actual location, it is found that the height in which up to which the effect of wall is penetrated, or the velocity gradient, you can see this represents del u by del r. Here you can see that the velocity gradient del u by del r is non-zero up to this height, and you have a inner radius where this region you have a constant velocity, and near to the wall again you have a velocity gradient. So del u by del r is 0 in the central region, but near to the wall there is a velocity gradient which sets in. As you move downstream, the height on which the velocity gradient is non-zero increases, whereas the central the central circular region on which the velocity is constant keeps on reducing. Further downstream, again the height of the velocity, the layer of the fluid in which your velocity gradient increases. So if you demarcate the region in which you have a velocity gradient as compared to the region in which you have a constant velocity in the central region, this demarcation is shown by this green line, which is called as boundary layer. So below this green line, you can see that there is a velocity del u by del r is non-zero, and in between these two green line, del u by del r at a particular axial location, it is 0. When the growth of the boundary layer is symmetric from the two ends of the wall, and this is the upper end and this is the lower end, and at a certain axial location, this boundary layer meets. Thereafter, the velocity gradients is found for a laminar flow to be a parabolic, and when the fluid moves downstream, it has been found that the fluid which is moving on a particular layer, its velocity remains constant. So you can see that the velocity profile after the boundary layer, the two boundary layer meets, this is called as hydrodynamically fluid developed region. In this hydrodynamically fluid developed region, the velocity profile do not change at the further downstream axial location. So if you consider at any radius, if you consider a fluid particle which is moving in a fully developed region, its velocity remains constant. Here, let's suppose in this radius the velocity is constant. In this radius also the velocity is constant. So del u by del x at any radius is equals to 0. So this is the characteristics of a hydrodynamically fully developed region. This is called as hydrodynamically developing region, and this LFT is called as development length. So when you consider flow in a uniform flow inside a pipe, there are two regions. Initially, there is a hydrodynamically developing region. Then the actual velocity profile reach to a velocity distribution which do not change in further downstream location, and after the velocity profile stop changing, after the actual location downstream of which the velocity profile stops changing, this is called as hydrodynamically fully developed region. You can see that this is the red line here corresponds to the average velocity. The inlet velocity, which is uniform, is also the average velocity of the flow in a pipe. So you can see this is the average velocity. So near to the wall, the average velocity is less than the velocity of the fluid inside the bound near to the bottom wall is less than the average velocity, and in the central region it is more than the average velocity. This is because due to the mass conservation, if you consider a control volume which is, let us suppose this is the left wall of the control volume, this is the right wall of the control volume, and the top and bottom wall is a solid wall. So if you apply mass conservation, the fluid cannot go out from the top and bottom wall. So whatever fluid is entering has to leave from this control volume. So for an incompressible flow, here we are considering an incompressible flow. If you take the integral of this integral of udr at various axial location, it has to be same. So you can see near to the wall, if you consider near to the wall and in the central region at the inlet, velocity is constant. And when you move downstream, near to the wall, velocity is slowly increasing from a zero value. So near to the center, for the volumetric flow rate conservation for an incompressible flow, the velocity needs to increase because the integral of this velocity profile needs to be conserved. If you take the integral of udr for this velocity profile, this velocity profile, this velocity profile, and the velocity profile at the inlet, they have to be same. So what you find is that there is a central region in which central circular region, which is the size of that central circular region is, I'm showing you an axisymmetric view for flow in a pipe. The size of that central circular region in which you have constant velocity is reducing along the flow direction, whereas near to the wall there is a region, the boundary layer region, whose thickness, the boundary layer thickness, which is shown here by delta, is increasing along the flow direction. So as I mentioned, that this is the central region where you have a core flow, where at a particular the velocity profile is you have a constant velocity in the central region. This velocity at this location, which are denoted here by u infinity 1, the inlet velocity is denoted here by u infinity 0. This u infinity 1 is greater than u infinity 0, and when you move further downstream, now you can see that the thickness of the boundary layer thickness has increased, and thickness of the core region has reduced. And so by mass conservation, this u infinity 2 should be greater than u infinity 1. So you can see that the size of these arrows as you move downstream is continuously increasing. So so the maximum velocity u infinity 1 is greater than u infinity 0, u infinity 2 is greater than u infinity 1, u infinity 3 is greater than u infinity 2. And finally, when the flow becomes fully developed for flow in a pipe, the fully developed maximum velocity profile is 2 times of the inlet velocity. So by volume conservation for an incompressible flow, if you take the integral of this velocity profile, and that will be equal to u infinity naught into pi d square by 4. If you take the integral of u 2 pi r dr 0 to r, if you integrate this parabolic velocity profile, it will be equal to u infinity naught into pi d square by 4. So as I mentioned, this is there is a thin layer near to the wall where you have a non-zero del u by del r. This is called as boundary layer region. And in the central circular region, there is a region where the fluid is moving with whose velocity is constant at along the radial direction, but as you move downstream, the axial velocity is continuously increasing. You can see here it is increasing from u infinity naught to 2 times of u infinity naught. So in the core flow region, the velocity, although in the core flow region, the axial velocity is not varying along the radial direction, but that velocity is increasing along the axial direction. So in the core flow region, the fluid is accelerating from u infinity naught to 2 times of u infinity naught when it becomes fully developed. So for the acceleration of the fluid, it needs certain energy, which is given. So there is, when the fluid uh, in the hydrodynamic developing region, to accelerate the core flow, this results in the drop in the pressure of the fluid. The pressure of the fluid, it also drops because due to the stickiness between the different layers of the fluid, and to maintain the no slip boundary condition, there is a velocity gradient which sets in. So this velocity gradient tries to drag the pipe along the flow direction, whereas so there is, near to the wall there is a shear stress which acts, and whereas the pipe the pipe tries to resist that. So there is a viscous force uh, which acts. So uh, the this viscous resistance also causes the decrease in the pressure along the flow direction. So when the fluid flows in a pipe, there is a pressure drop which occurs. That's why, to transport a fluid, which could be a liquid or a gas, from one place to another like a conveyor belt, we need to very commonly used pump, so that at the inlet we provide sufficiently large pressure, because when the fluid, which could be a liquid or a gas, enter inside a pipeline in the developing region, uh, the pressure the pressure drop occurs not only due to the viscous resistance, but it also occurs to accelerate the core fluid region. So in the developing flow region, the viscous resistance acts in the opposite to the direction of the flow, which is due to the stickiness between the different layers of the fluid, which resists the motion between the different layers of the fluid. Now the core flow is accelerating, so the actual momentum flow rate um, in the core flow region, when you take the axial momentum flow rate in the core flow region, at this location it will be given by rho into u infinity 1 rho into u infinity 1 into, if you take the area of this, let us suppose this is the radius, then you take the pi r square, u infinity 1 into rho into that radius pi r square will give you the mass flow rate, and when you take the product with u infinity 1, it will give you the axial momentum flow rate. So the axial momentum flow rate, as you move from one location to another location, the axial momentum flow rate is increasing. So the inertia force is, so the uh, so the inertia force is acting in the axial momentum flow rate is increasing. So inertia force is shown in the positive x direction, which is the axial direction, and the pressure force reduces along the flow direction. So when the pressure force is reducing, the pressure force is also acting in the positive direction, because you have more pressure at the inlet and less pressure at the outlet. So the net pressure force is in the positive x direction, the viscous force in the negative x direction. And as I mentioned earlier, that the drop in pressure is due to two reasons. One is to accelerate the core flow, and the second is to to overcome the viscous resistance that is encountered due to the because each fluid has certain stickiness between the different layer of fluid, which is represented by a thermophysical property called as dynamic viscosity. Once the flow has become fully developed, now you can see that there is no acceleration. Each layer is moving with the same velocity. So there is no change in the axial momentum of the fluid and fluid particle in the different layers, and in a laminar flow, fluid particle at a particular layer remains in that layer and it is moving with a constant velocity. So there is no change in the axial momentum flow rate. So the inertia force is equal to 0 in this case, and the pressure drop occurs due to the viscous resistance only. So once the flow becomes fully developed, and this, you can also note that the velocity gradients, once the flow becomes fully developed near to the wall, is since the velocity profile is invariant along the flow direction once the flow becomes fully developed. So if you determine the velocity gradient at the wall to calculate the wall shear stress, it is also invariant. So the viscous resistance once the flow becomes fully developed is constant. So there is a the pressure drop per unit length is also constant once the flow becomes fully developed. After presenting the flow development, in this slide I'll discuss the variation of wall shear stress and the pressure along the flow direction when the flow is developing and when it gets fully developed. But before that, let me first discuss the development length in a laminar flow versus a turbulent flow. So for a laminar flow, the expression for the fluid development length is given as it's approximately equal to 0.05 times of Reynold number into diameter. And for a turbulent flow, it is 1.359 into Reynold number to the power 1 by 4 into D. So if you consider the Reynold number of 2300, and this is the maximum Reynold number up to which you can have a laminar flow. So at this constant Reynold number, if we use the expression for laminar and turbulent flow and obtain the development length. So the development from the expression for laminar flow, you get a development length of 115 times of the diameter of the pipe. Whereas if you because this 2300 is you can consider it also as a lower limit for the onset of the turbulent flow. So if you substitute this into the expression for turbulent flow, the development length comes out to be 9.4 D. So you can see that there is a substantial reduction in the development length when the flow transition takes place from a laminar to turbulent. So, so the velocity fluctuations in case of turbulent flow leads to a large reduction in the development length. The wall shear stress is given by basically we calculate the shear stress at the wall, and the expression for shear stress is mu. You have to take the normal gradient of tangential velocity. The tangential velocity at the wall is the actual velocity u, and the normal direction is the radial direction. So if you take the normal gradient of tangential velocity is del u by del r. So the shear stress is given by mu del u by del r. When you want to calculate at the wall, the radius corresponds to r is equals to capital R, which is the radius of the pipe. So if we plot the, so this is what I was emphasizing, that for a laminar flow, the development length is much larger as compared to the turbulent flow. If you plot the variation of the wall shear stress along the axial direction, there is an asymptotic decrease, and then it reaches to a constant value. The reason it becomes a constant value, as I mentioned, that if you calculate del u by del r at this axial location, and then you can calculate del u by del r at r is equals to capital R, which is at the wall, you can see that the fact that the velocity profile is invariant, so the slope of this velocity profile at the wall is invariant. And when this slope is invariant, and this is a constant quantity, the wall shear stress is invariant, so it becomes a constant quantity in the fully developed region. Whereas in the developing region, the velocity gradients are at the wall is gradually reducing. So the variation of wall shear stress from the inlet of the pipe to the fully developed region is there is an asymptotic decrease and reaches to a constant value when it becomes a fully developed flow. Whereas when you plot the pressure drop is large in the developing region as compared to fully developed region, due to the fact that in the developing region, the fluid also spends some energy in accelerating the pore flow in the central region. So so if you draw, and so there is a decrease in the pressure, and finally it reaches to a linear variation. Once the flow becomes fully developed, the dP by dx becomes constant. The wall shear stress, the gradient of wall shear stress with x is equals to 0, but the gradient of pressure with respect to x is a constant. So per unit length of the pipe, which means that if the slope becomes constant, if dP by dx is constant, which means once the flow becomes fully developed, per unit length of the pipe, the pressure drop is constant. This is because when the flow becomes fully developed, there is a balance between the pressure force and the viscous force at the wall. And since the viscous resistance at the wall, which is the wall shear stress, is constant, the resistance is constant, so the decrease in the pressure along the axial direction is also constant. So this way, once the flow becomes fully developed, in the fully developed region, the change in the wall shear stress is equals to 0, and dP by dx becomes constant because the pressure per unit length experiences the same viscous resistance. So per unit length, there is a constant drop in the pressure. This I will also show mathematically in the upcoming slides. I'll discuss the friction factor, which are the engineering parameter commonly used for flow in a pipe, which corresponds to the non-dimensional pressure drop and non-dimensional pressure gradient and non-dimensional wall shear stress. In the previous topic on analytical solution for 2D fully developed flow in a pipe, although I presented the derivation, but for this topic I am presenting briefly in this slide. So if you consider the axial direction as x and the axial velocity as u, radial direction as r, and the radial velocity as v, once the flow becomes fully developed, the axial gradient of axial velocity is equals to 0. We are considering a steady state fully developed flow, and so if we start with and we are considering it's a two-dimensional flow, and we are considering that the flow is not varying along the azimuthal direction. So the flow, when we consider 2D, we mean it's an axisymmetric flow. So so for an axisymmetric flow, if we write the continuity equation, this is obtained from the mass conservation law. So del u by del x plus 1 by r del by del r of rv is equals to 0. This is the continuity equation in cylindrical coordinate system, and it is shown here for the axisymmetric 2D situation. Once the flow becomes fully developed, this del u by del x is equals to 0. And then you are left with del by del r of r into v is equals to 0. So which means that if you go to any axial location and apply at any constant value of x, del by del r of rv is equals to 0. So del by del r of rv is equals to 0. Let us suppose at this axial location, if it is the change in the product of the radius and the radial velocity on a vertical line in a pipe, in a horizontal pipe, is 0. So on this vertical line, we know certain location in which we know the v velocity at certain location. Like at the surface of the pipe, we know the v velocity is 0. And from this continuity equation, we are getting a conclusion that the product of r into v is 0 on this vertical line. If you go to any vertical, sorry, this is the developing flow region. Let me go to the fully developed region, because this we are obtaining analytical solution in the fully developed region. So, and like this is the fully developed region. So if I take on this vertical line, the product of r into v is equals to 0, that we have obtained from the continuity equation. Now there are certain locations at which we know the v velocity, which is at the surface of the pipe. At the surface of the pipe, small r is equals to the radius of the pipe, that is capital R, and v is equals to 0. So we know that at the surface of the pipe, r into v is equals to 0, and on this vertical line from continuity equation, the product of r into v is equals to 0. So once we know the product of r into v at one point on this vertical line, and if it has to be a constant, then v has to be 0 on the vertical line. If you go to a next another axial location, downstream axial location in the fully developed region, and apply the same whatever I've discussed in this actual location, you get V is equals to 0 on that vertical line. So at any actual location, from the continuity equation and using the no-slip boundary condition, you come to a conclusion that at any actual location in the fully developed region, V velocity is 0. So from that you get that variation of V with actual location and with radius is equals to 0. So which means that in fully developed region, the radial velocity is 0 and the actual velocity variation is given by this parabolic velocity profile. And this parabolic velocity profile is invariant along the actual direction, that is del U by del x equals to 0. So I started with the continuity equation and I showed you that in the fully developed region, the radial velocity is 0 everywhere in the fully developed region. Now let us apply the axial momentum equation. This is the axial momentum equation in an unsteady, two-dimensional unsteady state form, where the two dimension we are considering is the xr, this is the axisymmetric coordinate. The r is equals to 0 corresponds to the axis of the pipe, and the radius is this capital R is the radius, and this is the axial momentum equation, unsteady form. So when we consider a steady flow, this del U by del t is 0. So we are considering a situation where the velocity profile is invariant with respect to time. So that's why del U by del t is equals to 0. From fully developed condition in the fully developed region, note that here we are obtaining analytical solution for fully developed flow. So for a fully developed flow, del U by del x equals to 0. So this term will become 0. From continuity equation in the fully developed region, we have obtained V is equals to 0. So this term will be 0. When del U by del x is 0, del square U by del x square also becomes equal to 0. So the axial momentum equation, it gets simplified, and now you have only two terms. One is the pressure gradient and another is the radial variation of the axial velocity, which is shown here. Now this is the axial momentum equation. If you write down the radial momentum equation, which is shown here, that is for radial velocity V, then here for a steady flow, del V by del T is equals to 0. And since V is not varying with respect to x and r, so its gradient with respect to x and r, everywhere it is 0, and you are left with only one non-zero term. So the radial momentum equation gets simplified as del P by del R is equals to 0. So from the continuity equation, we have got V is equals to 0, and when we use the fully developed conditions, so when we use these two conditions, we got a simplified axial momentum equation and a radial momentum equation, where in axial momentum equation we have two non-zero term, and in a radial momentum equation we have a one non-zero term, which is shown here. So this is a simplified axisymmetric momentum equation. This is the axial momentum equation. This is the radial momentum equation. So here pressure is not varying with respect to r. So pressure is constant at any axial location. Pressure is only varying with respect to x. So this partial derivative can be converted into a total derivative, since the pressure is not varying in the radial direction. It's varying only in the one direction. So P is only a function of x. So this can be converted into a total derivative. And now in this you can see that you have one derivative with respect to another term, which is a derivative with respect to r. When you have a differential equation where one term has a derivative with respect to s, another term has a derivative with respect to y, then the summation of the two can be 0 only if they are of equal in magnitude but opposite in sign. So you can consider dp by dx is equals to constant, and basically now to obtain the analytical solution, you have a second order ordinary differential equation with a constant that to obtain an analytical solution, that you integrate with respect to dr twice, and you get two constant, and those two constant you obtain by using the boundary conditions that you know at the axis of the pipe, that is r is equals to 0. At the axis of the pipe you can see from this velocity distribution that if this is the u as a function of r, and at the axis r is equals to 0, you can see del u by del r is a del u by del r. The variation of u along the radial direction, it is 0. So del u by del r at x is equals to 0, and at r is equals to capital R, which is the surface of the pipe. You have the u and v is equals to 0. The axial velocity, the radial velocity, both are 0, since the wall of the pipe is stationary. So using this two boundary condition and solving the second order ordinary differential equation with a constant, considering this dp by dx equals to constant in the fully developed region, you obtain the analytical solution as for the axial velocity u as r square minus capital R square, which is the radius of the pipe, divided by 4 mu into dp by dx. Now, this is the expression to obtain the average axial velocity 1 by the area of the pipe, that is pi r square, integral of 0 to r u 2 pi r dr. So when you substitute this u is equals to r, this expression which was shown in the previous slide, which is derived in the previous slide, you finally obtain this u average equals to minus capital R square by 8 mu dp by dx. From this you can obtain dp by dx equals to minus 8 mu divided by r square into u average, which is seen here. From this derivation, you can see clearly that mu is a dynamic viscosity, which is a positive term. The radius is also a positive term. This u average axial velocity is also a positive term. So all these variables are positive. So dp by dx is a negative term. So which means that the change in pressure along the axial direction, the gradient dp by dx is negative, which means that the pressure is reducing along the length of the pipe. So this is like a mathematical proof which indicate that dp by dx is negative. The pressure is reducing along the length of the pipe as the fluid is entering into the pipe. If you convert, if you substitute this r square in terms of the diameter, dp by dx in terms of diameter comes out to be minus 32 mu by d square u average. So with this, I had shown you, I had first shown you the derivation of the axial velocity, then we had obtained the average velocity, and finally we obtained the pressure gradient in terms of the average velocity. Now, as an engineer, we are interested in knowing this engineering parameter, such as in this case, the pressure gradient and the wall shear stress. The pressure gradient and the wall shear stress are the two engineering parameters for this problem. And it has been, as I mentioned in my previous topic, on the differential analysis, towards the end I had a topic on non-dimensional study where I had emphasized that in fluid mechanics we present our results in a non-dimensional form. So the two engineering parameters which are of importance for flow in a pipe once the flow reaches to a fully developed situation are the pressure gradient and the wall shear stress. So the non-dimensional representation of this is called as friction factor. The non-dimensional representation of the pressure gradient is called as as shown here. Non-dimensional pressure gradient is called as Darcy's friction factor, which is presented in this slide. And in the next slide, I will show you the non-dimensional wall shear stress, which is called as a fanning friction factor. Now, for the non-dimensionalization, the pressure is non-dimensionalized with respect to the dynamic pressure given by 0.5 rho u average square, whereas the actual coordinate x is non-dimensionalized with the length scale, which is corresponding to the diameter. So this Darcy's friction factor symbolically is represented by small f. This is equal to minus dp by dx, where this small p is a dimensional pressure, this capital P is a non-dimensional pressure. The relationship between a non-dimensional pressure with a dimensional pressure is capital P is equals to small p divided by the dynamic pressure, which is represented here by half rho u average square. The capital X is the non-dimensional axial coordinate, which is given by the dimensional x coordinate divided by the length scale, which is a diameter. Whenever you solve a fluid mechanics problem, such as when you here solving a flow in a pipe, there is some velocity and some length scale which will at least one value of velocity and one length scale which will be given to you, which is characteristic of a problem. Like for flow in a pipe, the diameter is the characteristic length scale for the pipe. You are given the diameter of the pipe, so we take the diameter as the length scale. So so the non-dimensional axial coordinate is represented by small x divided by d. So this is basically equal to minus dp by dx into which is given here by minus 32 mu by d square u average. So here this is this is dp by dx. Actually, you have a minus sign outside, and this is minus, and then again a minus sign, so it becomes plus. So, the dimensional dp by dx is substituted from here, and then this d is taken into numerator. This half rho unit square is taken into denominator. So this dimensional dp by dx into for non-dimensionalization, this is the additional term which is coming. If you take the product of the two, you get this. In the denominator, you have d square, here you have d, so you get d cancels down. In the denominator, you get d, whereas this u average square, and here you have u average, so in the denominator, you get u average. So you get 64 mu rho u average d, and this rho u average d by mu is a Reynold number. So you finally obtain, but before I go into the expression, so basically f is equals to 64 divided by re, that's what you obtain. But note that Darcy's friction factor is minus non-dimensional pressure gradient, not plus non-dimensional pressure gradient. Okay, so the non-dimensional pressure gradient, the negative of non-dimensional pressure gradient is the Darcy's friction factor, and that is given as expressed for a laminar flow as 64 divided by Reynold number. We are able to derive this for a laminar flow, but later on I'll show you that for turbulent flow, we have to take the help of the experiment to, so this value is given from the experiment, and because since we are not able to derive it from the fundamental principles for a turbulent flow, which is a which involves velocity fluctuations which are random in nature. So we do not have an established theory for turbulent flow. However, for laminar flow, the derivation is presented here. So in the previous slide, I had presented the minus of non-dimensional pressure gradient as a Darcy's friction factor. In this slide, I am presenting the non-dimensional wall shear stress as a fanning friction factor. Now, in the previous slide, we have obtained the relationship between the pressure gradient and the average velocity. Now, in this slide, what we will do is that we will obtain a relationship between the wall shear stress and the pressure gradient in a fully developed flow region. So here I am showing you a control volume in a fully developed flow region whose axial length is delta x, and the cross-sectional area, note that this is the surface of the pipe. I am taking the length of the pipe, which is delta x, and the diameter of the pipe is d, and we are taking a control volume which corresponds to a pipe of length delta x in the fully developed region. This is the pressure acting on the left surface, Px. This is the pressure acting on the right surface of the control volume, Px plus delta x. This is surface x equals, this is surface x, this is the surface x plus delta x. The length is delta x. So the pressure acts normal to a surface. So, and in a fully developed flow region, pressure is not varying within the radial direction. It is varying only in the axial direction, as shown in the previous slide. So this is the variation. This is the pressure which is acting in the horizontal direction. Pressure acts normal and it is compressive. Now, near to the wall, the fluid tries to take the surface along its flow direction, whereas the solid surface tries to resist that motion. So at the surface of the control volume, the wall shear stress acts in the negative x direction. Note that this wall shear stress is acting on a surface which is which is on the circumference. So it is the area on which this wall shear stress is acting is pi d, whereas the pressure is acting in the cross section. So the area of the cross section is pi d square by 4. So if you calculate, if you do the balance of the forces acting in the x direction, so basically the net pressure force acting in the positive x direction should be equal to the net viscous force acting in the negative x direction. So the net pressure force acting in the positive x direction is Px minus Px plus delta x into pi d square by 4, whereas the net shear force which is acting in the negative x direction is tau w into pi d. So the pressure is acting in the cross-sectional area and the wall shear is acting on the circumference pi d delta x. So, so if you take the delta x in the denominator and apply the limit, here you will get, so it will be px minus px plus delta x. If you take delta x in the denominator and use delta x tends to 0, you get minus del p by del x. This pi cancels down. Here you have d squared, d square term cancels down, and here you get d by 4. So you get tau w is equals to minus dp by dx into d by 4. So using a control volume analysis, a finite control volume of corresponding to the complete cross section of the pipe, but the length of the pipe is delta x. Here we have obtained a relationship between the wall shear stress and the dimensional pressure gradient. And in the previous slide, we have an expression for dp by dx in terms of the average velocity. So we will substitute that expression here, and finally we will obtain an expression for non-dimensional wall shear stress. Wall shear stress is non-dimensionalized with the same quantity which is used for pressure. Note that the unit for the pressure and the pressure is also a stress, force per unit area. So the unit of pressure and wall shear stress is same. So it is non-dimensionalized by 0.5 rho. This should be U average square, not W average. There's a mistake here. So so when you, so this tau W is non-dimensionalized by, this is the non-dimensional form is called as this non-dimensional wall shear stress is called the fanning friction factor. So this P, when you divide by 0.5, so what you can do is that tau W we are dividing by 0.5 rho U average square. So I can write P divided by rho U average square, which is the non-dimensional pressure, and I can take D from the numerator to the denominator as shown here. So when I take D to the denominator, I'll get 1 by 4. So this becomes a non-dimensional pressure gradient now, because this is a capital P and this is capital X. So I can write Cf is equals to minus d capital P by dx into 1 by 4. This dp by minus dp by dx is the Darcy's friction factor. So here you can see that the fanning friction factor is 1/4 of the Darcy's friction factor. I have shown in the previous slide that the Darcy's friction factor is 64 by Re. So 1/4 of it results into the fanning friction factor as 16 by Reynold. So in the previous slide, I had shown you the negative of non-dimensional pressure gradient called as Darcy's friction factor. I had shown you the derivation where F is equals to 64 by Re. Here for non-dimensional wall shear stress, first I have, using a control volume analysis, I have derived an expression between the dimensional wall shear stress and dimensional pressure gradient. Then we had converted into a non-dimensional form and finally obtained the non-dimensional wall shear stress called as fanning friction factor, denoted by Cf is equals to 16 by Re. Note that this is for laminar flow in a pipe. After deriving the non-dimensional expression for the pressure gradient and the wall shear stress, now I'll present the pressure drop, the head loss, and the pumping power. So there's a drop in the pressure that we have mathematically seen, that dp by dx is negative, and the pressure due to this pressure drop in a fully developed flow is due to the viscous resistance, which is constant per unit length of the pipe. That's why dp by dx is constant. And due to this friction, this is normally we in the previous topic on Bernoulli's equation, I had mentioned that the pressure can be expressed in different types of quantities. So we also express pressure in terms of head by dividing by rho g. So the pressure drop that occurs due to the viscous resistance in for flow in a pipe, if you divide that pressure drop by rho into g, you can get a term which is called as head loss. This head loss indicates normally we use pipe to transfer, let us say, liquid from a smaller height to a larger height. So this gives you an idea that the viscous resistance leads to how much loss in the height by which we could have transported the fluid. So the pressure drop is converted into a head loss that will be presented in this section. And finally, once you know the pressure drop, to calculate the power from which we obtained the pumping power, because for transportation, since we need to ensure that at the inlet of the pipe we have provided sufficient pressure, so we need commonly used pump. So the power for pump is decided so pumping power is given by the product of the pressure drop multiplied by the volumetric flow rate. So first I will show you the expression for pressure drop, then head loss will be given by the pressure drop divided by the density rho into g, and the pumping power will be the pressure drop multiplied by the volumetric flow rate. So this is a pipe of diameter d, and we are considering that the flow is fully developed along the length of the pipe. So we are taking a section of the pipe corresponding to the fully developed flow. Pressure at the inlet is shown here as P inlet. This is the pressure at the outlet. In the previous slide, I had shown you F is equals to minus of non-dimensional pressure gradient, where if you write in terms of dimensional pressure gradient, it is given like this. This dP by dx is pressure at outlet minus pressure at inlet divided by the x location at the outlet minus x location at the inlet, which is L. So dP by dx is given as P outlet minus P inlet divided by the length of the pipe. Now, when we talk of pressure drop, it is here it is written outlet minus inlet, but when we talk about the pressure drop, it is inlet minus outlet. So the negative of outlet minus inlet is delta PL, which is given as this. This pressure drop is expressed in terms of friction factor as delta PL is equals to F into L by D, as shown here. F into L by D into rho U average square divided by 2. So this is the expression for pressure drop. Pressure at the inlet, which is more, minus pressure at the outlet. Now, to obtain the head loss, we divide this pressure drop by rho g. So this is the loss of the head or height which could have been used for lifting the fluid from lower level to higher level. This is a loss in overcoming the viscous resistance, because as I mentioned, different fluids have, due to the random motion of the molecules, they have certain stickiness between the different layers of the fluid, for which when the fluid tries to flow in a liquid, it has to overcome that viscous resistance that leads to this head loss. In a fully developed flow, the head loss is given as when you divide by rho g, then you get rho cancels down and you get FL U average square divided by 2GD as shown. This expression is commonly used in numerical problems for flow in a pipe or pipe networks. After the head loss, the expression for pumping power, as I had mentioned earlier, it's equal to pressure drop multiplied by the volumetric flow rate. So this V dot is the volumetric flow rate. Now this delta PL is equals to rho G HL, and rho into volumetric flow rate is mass flow rate. So the pumping power is expressed in terms of mass flow rate into G into head loss. Now this now I'll show you the expression for volumetric flow rate, which is commonly used for flow in a pipe. This expression for volumetric flow rate is also called as Poisson's law. So the expression for volumetric flow rate is given as a product of the average axial velocity multiplied by the cross-sectional area. The average axial velocity we have obtained from here. You can write in terms of the pressure drop. The Q average is equals to delta PL d square by 32 ml, and area is pi d square by 4. So the volumetric flow rate comes out in terms of the pressure drop, the diameter of the pipe, the length of the pipe, and the viscosity. Now, this expression is special in a sense that it is also called as a Poisson's law, because from this expression you can conclude that if you want to deliver a fluid at a certain fixed rate, like if just to give you an example, let us suppose there is an oil field and you want to deliver from one place to another the oil at a constant rate, then the question is that so if you are having a particular fluid, your viscosity is fixed. However, you would like to know that to deliver, you would like to have the least pressure drop. So let us suppose you want to design the pipe so that you have a least pressure drop. So that way this expression is special and it is called as Poisson's law. Like, so for a constant volumetric flow rate, from this expression you can see that the pressure drop is directly proportional for a constant volumetric flow rate. Delta PL, the pressure drop, is directly proportional to the viscosity of the fluid, the length of the pipe, and it is inversely proportional to the diameter of the pipe. So you can see that for a constant volumetric flow rate, the pressure drop is inversely proportional to the fourth power of the diameter, which means that if you want to have this V dot as constant, and you can, if you, let us say, double the pipe diameter, then you can reduce, since the pressure drop is inversely proportional to d to the power 4, if you can double the diameter, you can reduce the pressure drop by 16 times for the same volumetric flow rate. Okay, so you can reduce the pumping power by a factor of 16. So for a specified flow rate, the pumping power requirement for a laminar flow system can be reduced by a factor of 16 by doubling the pipe diameter. Till now I have presented for flow in a circular pipe, but as an engineer we encounter internal flow situation where the cross section is non-circular. So here I am showing you the friction factor for non-circular pipe. I am not showing you the derivation. I will show you the final expression that has been proposed in the literature, and these are the expressions which are given in the textbook on fluid mechanics by Singhal and Simbala. So for a circular pipe, I have a pipe of circular cross section. I have shown you the derivation 64 by RE. Whereas for if you have a rectangular duct or a rectangular pipe of a rectangular cross section, or a pipe of elliptic cross section, or isosceles triangle cross section, and here for a rectangle you can have different aspect ratios where you have different width as compared to height, A by B. So if you keep on increasing A by B from 1 to infinity, infinity becomes a parallel channel. parallel flow in a parallel channel. You can see that in circular pipe you have 64 by Re, and here as you keep increasing this width, the denominator value increases from 56.92 to 96.0. And here in ellipse, when you increase the width as compared to height as shown here, varying from 1 to 60, here again the numerator changes from 64 by Re to 78.16 Re. These are the friction factor values corresponding to the isosceles triangle, where this angle theta is varying from 10 to 120 degree, corresponding to 5 different value of theta. The expression for the friction factor is shown here. But one of the question is that what should be the length scale? Because to calculate the Reynold number, the common thing is that the average velocity. But in a pipe, you have one length scale, which is the diameter. But when you look into this cross section, you have more than one geometrical dimensions. Like in a rectangular duct, you have a width and the height of the duct. In the ellipse, you have a major axis and a minor axis. And so what should be the what should be the length scale that you will consider to calculate the Reynold number? For a flow in a pipe, we have taken the diameter as the length scale. So for non-circular pipe, it has been suggested that the characteristic length scale is obtained by using a hydraulic diameter, which is given in terms of 4 times of cross-sectional area divided by the perimeter. So the Reynold number for non-circular pipe, the characteristic length scale is called as a hydraulic diameter, and that hydraulic diameter is expressed as 4 times of cross-sectional area divided by perimeter. Just to give you an example, for flow in a pipe, area is pi by 4d square and the perimeter is pi d. And if you take the ratio, you get dh is equals to d. If you have a square duct, then this becomes 4, the cross-sectional area is a square and the perimeter is 4a. So 4a by p is 4a square by 4a, and if you divide, you get a as the hydraulic diameter. And for a rectangular duct, the hydraulic diameter, the area is a into b and the perimeter is 2a plus 2b. When you take the ratio, you get 2ab divided by a plus b. So note that if you have to solve a numerical problem which corresponds to a non-circular duct, then first you have to obtain the hydraulic diameter and then calculate the Reynold number. And if it's a laminar flow, once you know the Reynold number, then you can use the appropriate expression corresponding to the non-circular pipe and the geometrical dimensions which are given to you, and obtain the friction factor, which corresponds. Note that this friction factor which is presented here is small f, which is corresponding to Darcy's friction factor, not the fanning friction factor. So after the laminar flow in a pipe, let us move to turbulent flow in a pipe. So I'll first start with a general introduction of turbulent flow. Then I'll go into the laminar versus turbulent flow velocity profile. And finally, I'll present the friction factor. As I mentioned earlier, that we have an established theory for laminar flow from which we have derived the expression for friction factor, which is not the case for a turbulent flow. And for this, the friction factor values which will be presented has been obtained from the experiment, and certain correlation, empirical correlation will be presented along with a figurative representation for turbulent flow in a pipe. So note that for turbulent flow in a pipe, we do not have an analytical solution for the friction factor, as in contrast to the laminar, where we can derive the expression for friction factor. Darcy's friction factor is 64 by Re, Finite friction factor is 16 by Re. Turbulent flow is the mostly encountered flow in engineering practice. So as an engineer, most of the time we encounter velocities and length scale which corresponds to a turbulent flow. These are characterized by random and rapid fluctuations of swirling regions in a flow called eddies. And this velocity fluctuations provides an additional mechanism for momentum and energy transfer. Theory for turbulent flow remains largely undeveloped, as I mentioned earlier. Therefore, we have to rely on experiments, and the resulting empirical or semi-empirical correlation have been developed for various turbulent flow situations. Note that the turbulent flow is associated with large values of wall friction, the viscous friction, and it leads to large rate of heat transfer and mass transfer coefficient. If you compare, let's consider flow in a pipe, and if you compare the laminar velocity, fully developed velocity profile versus turbulent fully developed velocity profile, what you observe is for turbulent as compared to laminar flow, the velocity gradients at the wall and thus the wall shear stress are much larger. Okay, so this is the case for flow in a pipe, but let's suppose if you consider flow over a flat plate, in that case also the near to the wall in a turbulent flow you have a large velocity gradient. However, the boundary layer that goes over a flat plate is thicker for a turbulent flow as compared to laminar flow for the same value of the free stream velocity for flow over a flat plate. This is the velocity profile which has been shown for a fully developed velocity profile for a laminar flow, and this is the velocity profile for a turbulent flow. Let us say we have this velocity profile has been shown near to the transition value at a so that the volumetric flow rates are almost same, corresponding to let us say Reynold number of 2300. So what I want to emphasize here is that if you compare the laminar flow versus turbulent flow near to the wall, you can see that the velocity gradient, the slope of the change in velocity del U by del R for a turbulent flow is much larger as compared to that for a laminar flow. The primary reason is in a turbulent flow. In a laminar flow, let us suppose the fluid is moving on this horizontal layer. The normal velocity, which is a radial velocity, is zero in this case. Whereas when you look into a turbulent flow, along with the axial velocity, there is a radial velocity, and that too, although the time averaged value of that radial velocity may be zero, but you have a time-wise varying radial velocity. At some time it may be in the upward direction, and some time it may be in the radially downward directions. So this fluctuating transverse velocity, the fluctuating V velocity, what it causes is that it causes a fluid particle to move from a particular layer to a layer above or below. So such as if you consider, let us suppose this layer, and if a fluid particle moves to an upper layer, which is moving at a larger velocity, then what it does, it tries to reduce the velocity of the upper layer. If it moves to a lower layer, then it tries to increase the velocity of the lower layer because the lower layer is moving with a smaller velocity. So a fluid particle in a particular layer, due to the radial velocity, at certain times it moves up, where it tries to reduce the upper layer velocity. At certain other time, if the radial velocity is downward, it moves downstream and try to increase the axial velocity. So what I'm trying to say is that the axial momentum flow rate, there is a mixing, and the velocity profile becomes much flatter. So near to the center, you can see when you compare the laminar versus turbulent, the central region corresponds to a fully turbulent flow region. In a turbulent flow also there are various regions. Near to the wall, you have what is called as the viscous sublayer, but in the central region, you have a fully developed turbulent flow. So near to the wall, the viscosity is dominant, and there is an intermediate region called as buffer layer and overlap layer, which is like a transition layer, and in the central region, which is called as farthest from the wall, you have a fully turbulent flow region, and in this fully turbulent flow region, you can see that the velocity gradients are much flatter. This is the average velocity. When you compare the average velocity, you can see that the maximum velocity in a turbulent flow is slightly more than the average velocity, whereas for flow in a pipe, I had mentioned that the maximum velocity is 2 times of the average velocity. So the turbulent flow leads to the intense So this is there is a spelling mistake. Then the intense mixing in turbulent flow brings fluid particles of a different momentum in the different horizontal layer into close contact and thus enhances the axial momentum transfer. So if you see the variation in the axial momentum between the different horizontal layer in the central region is less as compared to the laminar flow, because there is an intense mixing in the turbulent flow, and that leads to a much flatter velocity profile in the central region. However, if the volumetric flow rate is constant, let's suppose corresponding to Reynold number of 2300, then if the velocity is low here, near to the wall, the velocity is to increase sharply, and for the integral of udr to be same in both the cases. So the velocity gradients are much larger in the turbulent flow as compared to that for a laminar flow. And when near to the wall, velocity gradients are larger, del U by del R is more at wall, you have a larger wall shear stress. Uh, For a laminar flow, I had shown you the analytical expression, but in a turbulent flow, as I mentioned, that people have done experiments, and this is one of the common expression which has been obtained from the experiment, where friction factor is related with this epsilon is the roughness of the pipe, d is the diameter, and r is the Reynold number. So this equation was proposed by Colebrook in 1939. However, instead of using this equation, what has become more popular is to calculate a friction factor is this figurative representation of the friction factor. So for a turbulent flow, we use this figure very commonly, and this represents a graphical form of the F. So what I'm saying is, although the equation for friction factor was proposed earlier, but later on, this was proposed in 1939, but later on, there is a graphical form of the friction factor which was proposed by Moody in 1944, and this is called as Moody's chart, which is commonly used, where basically in the x-axis you have a Reynold number, and in the y-axis you have a friction factor. And in this graphical form, it is shown for laminar as well as turbulent and the transitional regime. So in the laminar regime, you can see that this is corresponding to the relationship F is equal to 64 by Re. So as Re is increasing, the friction factor is reducing. And another point to note is that when the flow becomes fully turbulent, the friction factor depends on the roughness of the pipe. For a laminar flow, the friction factor is independent of the roughness of the pipe. But for a turbulent flow, it has been found experimentally, because when you consider the pipe of different material, they have a different roughnesses, and based on the roughness, um, the the friction factor varies is a function of the roughness for a turbulent flow, but not for a laminar flow. Another point to note is that the variation of F versus Re in laminar flow is inversely proportional, and you have a decreasing trend, whereas in case of turbulent flow, for rough pipe, there is an asymptotic decay. So there is a decrease in the friction factor with increase in Reynold number, and after a certain critical Reynold number, the friction factor reaches to a constant value. So it asymptotes, and for a turbulent flow in a rough pipe, the friction factor becomes independent of Reynold number at larger Reynold number. Okay, so this dotted line represents the Reynold number after which the friction factor becomes almost horizontal, and it becomes independent. The friction factor becomes independent of the Reynold number. You can see that this epsilon by d is equal to 0 is corresponding to a smooth pipe, in which case it doesn't reach to a constant value, whereas for rough pipe, this is the roughness epsilon divided by d, where d is the diameter of the pipe, is equals to 1 into 10 to the power minus 4. This is 1 into 10 to the power minus 3. This is 1 into 10 to the power minus 2. So as the roughness is increased, you can see that the friction factor is increasing with increasing roughness value. This expression was proposed by Colebrook, but when you look into this equation, you see F on the left hand side as well as on the right hand side. So this is an implicit equation. Later on, an explicit equation for the friction factor was presented in 1983 by Holland, and this is accurate within 2% of the Colebrook equation. So here you have F only on the left hand side. This is an explicit equation, and it is easy for calculation. So if you are given a Reynold number, the roughness of the pipe and the diameter, you can use this to calculate the friction factor from this equation. However, more commonly, people use this graphical form of F, which is called as Moody's chart, to calculate the friction factor for a turbulent flow, and depending on the roughness. So once you know the Reynold number and roughness value, you can use this chart to read the value of friction factor, and instead of using so note that in laminar flow we have derived 64 by RE as the friction factor, whereas this is not obtained from a derivation. It has been obtained. People basically did experiments. They measured the value of the friction factor. Then basically using curve fitting, they came up with this expression for the friction factor in terms of the roughness and the Reynold number. So the experimental results can be either presented by curve fitting in a form of an equation, or it can be expressed in a graphical form, which is presented here as Moody's chart, and this is most commonly used nowadays for calculating friction factor for a turbulent flow. Now, when you look into the problems for turbulent flow in a pipe, there are three types of problems which are commonly given. In all these three classes of problems, you are given a particular fluid and you are also given the roughness of the pipe. The first type of problem is you have to determine the pressure drop or the head loss when the pipe length and diameter are given for a specified flow rate. It could be mass flow rate or volumetric flow rate, or you are also, instead of, if the flow rate is not given, you are given the average velocity. So if you are given the average velocity and if you are given the diameter, and if you also know the fluid, then you know the density, viscosity, you know the diameter, you know the velocity, then you can calculate the Reynold number. Once you know the Reynold number, you are given the roughness, epsilon, you take the ratio epsilon by D. So once you know the Reynold number and epsilon by D, you can use the Moody's chart as shown in the previous slide. Once you know the Reynold number, if you know the diameter, average velocity, the fluid, you can calculate the Reynold number. If the roughness is given, you know epsilon by D. And once you know epsilon by D, so let's suppose epsilon by D is this and Reynold number is this, so you can pick this value as the friction factor. This way you can calculate the friction factor. This is a direct method. The other two methods are indirect in a sense, because in those cases you are not given sufficient data to calculate the Reynold number. In the second class of problem, you have to determine the mass flow rate when the pipe length and diameter are given for a specified pressure drop. It is like if you have got note that when the fluid leaves, let's suppose if you consider flow of water from a pipe. Now when the fluid leaves the pipe, if it is leaving under atmospheric condition, at the outlet, note that the pressure is atmospheric. So let us suppose if you are having a pump where at the inlet of the pipe, depending on the capacity of the pump, you have a constant pressure at the inlet of the pipe, and at the outlet it is atmospheric pressure. So once let us suppose you have purchased a pump, you have a constant pressure drop, and you want to know what will be the mass flow rate that is obtained. If you let us suppose you have a pump, you also have a pipe of certain length and diameter, and you want to know what is the mass flow rate. Now, in this case, note that if you don't know the mass flow rate, you don't know the average velocity, and if you don't know the average velocity, you cannot calculate the Reynold number. So this is a problem which is iterative in nature. And in the third problem also, again, the same issue is that in this case, you have to determine the diameter of the pipe, and if you don't know the diameter of the pipe, you don't know the length scale, and you cannot calculate the Reynold number. And so this is like a geometrical problem where you have to obtain the pipe diameter, then the pipe length and the flow rate are given for a specified pressure drop. So this is like a design problem where we want to know what will be the best diameter of the pipe which will lead to, let us say, least pumping power. Um, but here in this case, you are given a specified pressure drop, but you can use it as an optimization problem also. But in this case, again, as I mentioned, that if you don't know the diameter of the pipe, you cannot calculate the Reynold number. So that way you cannot directly use this Moody's chart and obtain the friction factor. So in this third class of problem also, you have to solve it in an iterative, by an iterative method. However, later on, instead of using the Moody's chart, people have come up with mathematical expressions, simplified form of the mathematical expressions, where they have proposed explicit equations for the second and the third class of the problem, which is presented in the next slide. For a non-iterative explicit equations, Swami and Jain in 1976 has presented the equations for the head loss, which is given by head loss in terms of the volumetric flow rate. This is the roughness of the pipe and this is the diameter of the pipe. This is the expression for explicit equation for the head loss. Although in this case, you can use the Moody's chart directly because you don't need to solve it iteratively. Whereas for the other two cases, when you have to obtain the volumetric flow rate, this is an expression to explicit equation which you can use where the volumetric flow rate is on the left hand side. So in the second class of problem, which I have shown in the previous slide, where you are given the diameter of the pipe, the length of the pipe, and the head loss, you can use this expression to obtain the volumetric flow rate. Whereas for the third problem, where you have to determine the diameter of the pipe, this is the explicit equation that you can use rather than solving iteratively. So for the type 2 and type 3 problem, you can use this equation and avoid the iterative method. You can using this equation, you can solve directly to obtain the volumetric flow rate for the second type of problem and the diameter of the pipe for the third type of problem. Finally, after presenting the friction factor for the laminar flow and turbulent flow, I have presented the friction factor, two types of friction factor, Darcy's and Fanning for the laminar flow. For the turbulent flow, I have only presented the Darcy's friction factor, which corresponds to the non-dimensional pressure gradient. Now, whenever you have a piping arrangement, as I mentioned, that the pipe acts like a conveyor belt to transport liquid from one place to another. Now, when you want to transport, when you have a pipeline, then it has to undergo certain connections because from one region to another, it always doesn't go on a straight path. Sometimes it has to bend, and many times you also need certain walls for opening and closing. So depending on the pipe connections and the walls, and many times you have to increase the diameter of connect two different pipes of different diameters. So you have certain joints. So for joints and the connections and the walls, this also leads to certain pressure loss. So the losses which were presented till now for laminar and turbulent flow, those are called as major losses, because as compared to these connections, the pressure drop for flowing laminar and turbulent pipes are much more as compared to the losses in these connections. So the losses corresponding to these connections and walls are called as minor losses. And these minor losses are basically expressed in terms of dynamic pressure, rho u average square by 2, where so there is a constant of proportionality which is used. So I'll present that. So as compared to the total head loss in a pipe, losses through various fittings like walls, bends, elbows, T-joints, inlet, exits, enlargement, and contractions, we have pressure drop, which are called as minor losses. So the minor head loss is quantified in terms of loss coefficient. So as I mentioned that, again, this has been obtained from experiments for various fittings walls bends elbows, as I mentioned earlier. The minor head loss, basically by doing an experiment, people first obtain the head loss and they already know the average velocity in the pipe, and they use this expression which corresponds to um, the pressure loss is KL into U square half rho U square, but to obtain HL you have to divide by rho G. So U square half rho U square, when you divide by rho G, it becomes half U square by G. So head loss is, and this is the constant of proportionality. So this is the loss coefficient which have been obtained experimentally for various types of fittings, pipe fittings and walls. And so if you consider uh, various connections of the pipe and maybe pipes of different diameter, sometimes you have to connect smaller pipe with a larger pipe using enlargement and vice versa with the contractions. So let us suppose you have many pipes and you have many pipe fittings. So let's suppose you have I number of pipes and j number of pipe fittings. And for I number of pipes, for each pipe, you can calculate the head loss by using this expression FL U square by 2GD. The I is the number of the pipes and J is the number of the fitting. For each fitting, basically use the average velocity of the fluid in the corresponding pipe divided by 2G, and this are loss coefficients which have been obtained from the experiment, which is presented here. This is the loss coefficient. So suppose this is a overhead tank or a dam, and this is a pipe from which the water is coming out, and there could be various types of exit. You can have a pipe connection like this, you can have a pipe connection like this. Here there is a sharp turn, and here if you have a smooth turn. So this is called as a re-entrant case. Pipe inlet is re-entrant. Fluid is first entering into the pipe and then it is coming out. So in this case, the head loss is 0.8. And when you have a sharp edge, the head loss is 0.5. Head loss coefficient is 0.5. When you are well-rounded, the head loss coefficient, if you have low radius, then your head loss coefficient is more. If your radius increases, the head loss coefficient increases. Now, I will show through a figure when you have sharp entry, basically there is a flow separation and there is a recirculating flow region which forms because the fluid cannot suddenly turn 190 degree. So the fluid which is coming, it goes into this path. So there is a region in which the fluid circulates, such as in this case, it is circulating in the anti-clockwise direction. Here it is circulating in the clockwise direction. So this is the recirculating flow region which leads to the pressure loss. So in these cases, you have a larger pressure loss. So, whereas if you have a well-rounded entry, the fluid which is coming doesn't find a sudden turn and it can gradually maneuver the path. So in this case, you can see that the loss coefficient reduces as low as 0.03 and for a sharp turn, it is as high as 0.5. There is a figure for various, as you keep increasing the radius, this radius for the 90-degree turn, if you keep increasing the loss coefficient, in the variation of loss coefficient with increasing rounding radius is shown by this figure. If you consider, if you have a smooth 90-degree turn, we call it as an elbow, and if this elbow is connected to the pipe through a flange joint, in this case the loss coefficient is 0.3. If you have a sharp turn, the loss coefficient is 1.1. You can have pipelines which has a gradual expansion, or you can also have pipelines where you have a contraction, and if the expansion angle is 20 degree, 45 degree, 60 degree, these are the loss coefficient which have been obtained from the experiment. And when you have the contraction angles, for contraction angle of 20 degree and for various reducing ratios, These are the loss coefficients which have been obtained from experiment. So we use this loss coefficient corresponding to a particular situations which have been reported in the literature, and then calculate the minor loss and add it to the major loss corresponding to the head loss for flow in a pipe to obtain the total head loss, which makes us decide the capacity of the pump for a particular application. Now finally, for various pipe fittings and walls, this slide shows the loss coefficient which has been again obtained from the experiment. This is for bends, and in bends you can have different types of joint, flange joint or a threaded joint, and that leads to a different loss coefficient as shown here. For a flanged, the loss coefficient is 0.3, for a threaded it is 0.9. This is a smooth bend. If you have a sharp bend, then this is the loss coefficient. If you have a sharp bend, but if you have a veins or blades inside, then the loss coefficient reduces. If you have a 45-degree threaded elbow, then the loss coefficient is 0.4. For 180-degree bend, if you have a flanged joint connection versus a threaded connection, these are the loss coefficients. If you have a T-joint and the fluid has to go from horizontal to vertical direction, for a flange joint and threaded joint, these are the loss coefficient. If the fluid has to go inline, then these are the loss coefficient for flange and threaded. If you have two pipelines connected by threads, this is called as threaded union. In this case, experimentally the loss coefficient has been found to be 0.08. You need valves for opening and closing, and depending on how much the valve is open, there are different loss coefficients. So this is for a globe valve, angle valve, ball valve. The loss coefficients are shown here. This is for swing check valve. For various gate valve, fully open, the loss coefficient is 0.2. If it is 1/4 closed, note that the loss coefficient increased to 0.3. If it is half closed, it is further increased to 0.1. But if it is 3/4 closed, the loss coefficient reduces to increases further. So this is 17. So when you increase the closing, the loss coefficient you can see it increases from fully open, it is 0.2. When you have 3/4 closed, it increases up to 17. With this, I have come to the end of this lecture. Whatever I have covered, you can refer this book, Singhal and Simhala. Thank you for your attention.